So yeah, my title, firstly, thank you to the organizers for giving me a chance to speak. And the title I'm going to be talking about is Complex AdS Black Holes and Thermodynamics. This is some work in progress with Raghu. And since it's a short talk, I'll really skip over the AdS part. I'll actually not talk about it at all. I'll talk very little about black holes. I'll just focus on the thermodynamic aspects of the problem. A very short two-line summary of what I'll be talking about is basically considering statistical systems which have which you can write down a partition function which seemingly have some spurious contributions. Some things that should not have been there can contribute, naively speaking. And our goal is to explain these contributions and why they are not really there. Okay. So black holes, simply said, they are just some solutions of Einstein's equation which have some additional causal property. And it was shown some time ago that the evolution equations of black holes are very similar to thermodynamic laws that we know from century ago. And this resemblance is not just in form. You can actually put this more precisely by mapping the parameters that describe a black hole solution into intensive variables of a thermodynamic system and mapping the charges that the black hole carries into extensive variables of a thermodynamic system. And the fact that there's a thermodynamic resemblance of these laws begs the question whether you can interpret this full system as statistical, as a statistical ensemble of some microstates. To paraphrase this question, you can ask whether there's a partition function description of the thermodynamics so that you can probe the microscopics a little better. And the answer is that in some cases you can do this. And the one way to do this is called the Euclidean approach, which was presented by Gibbons and Hawking, that you write down a path integral for this full partition function. It's some infinite dimensional integral over all the field variables weighted by some action. And from an analysis point of view, this is quite complicated to deal with. But luckily, there are often reductions to a more simpler integral. In the case of black holes, this reduction looks like some falling finite dimensional integral, where you can approximate this full thing by a smaller integral, where you just integrate over black hole parameters. And the weightage is something very similar to what we encounter in statistical mechanics, right? It's just the Boltzmann weighting with some e to the s density of states. And since this is a familiar form of partition function, from this stage forward, you can practically forget about the fact that we were looking at black holes. It's just an ordinary statistical system from now on. But nonetheless, it's good to keep in mind that we are talking about black holes. And we'll just pretend that these parameters seem to label some microstates, even though that's not the physical picture. Okay. So let's discuss that thing in an example. If you take a Schwarzschild black hole, and which is nothing but a spherically symmetric solution of Einstein's equation with no additional charges, and it's a static solution. Its metric is completely characterized by a single parameter, the horizon radius. And the charges that it carries are simply the mass of the black hole and the area of the black hole. These enter the evolution equations of black holes. And the thermodynamic description, as I told you, involves converting the black hole parameter, the horizon radius, into the one of the intensive variables, which in this case is temperature. And you convert the charges into some thermodynamic quantities, the energy of the system and the entropy of the system. And this is the precise relation. Now, the question we were trying to ask is whether we can encode this in a partition function kind of description. And the answer, as I told in the previous slide, was that you integrate over the black hole parameter of this Boltzmann kind of weighting. And I'll rewrite this as some lambda times the potential, where lambda is some inverse g Newton, which is really a large parameter. So we'll study this integral in a large lambda limit. And the potential in the specific case is basically a quartic potential with parameters in terms of the inverse temperature beta. Inverse temperature itself is chosen freely at this point. And what happens is that since we are doing a large lambda analysis, we'll basically try to analyze this integral using its saddle points, where we find the critical points of the potential V, and at that solution, see what's happening. And at those critical points, expand the integrand. We notice that there's a trivial saddle at the origin. And this, physically speaking, it corresponds to just a vacuum solution with just some thermal gas in equilibrium. And there are these additional saddles for which you recover the thermodynamic relation between the inverse temperature and the horizon radius. And this is how really the partition function is encoding this thermodynamic relations. You feed in the Boltzmann weights accordingly by getting the macroscopic charges of the black hole. And when you do a saddle analysis, you recover the relation between intensive variables and the parameters of the black hole solution. Now, naively, whenever you do a saddle point analysis, you expect that the dominant thing will be coming from the minimum of such a potential, because that is the maximum contribution that can appear in this integral. And you'll mostly be right, but you still have to be careful about certain subtleties. But let's look at this in more detail. So if you plot the potential versus the horizon radius for different values of beta, varying values of beta, at smaller beta, so this is a plot with increasing beta in the right. So if at very small beta, you'll always get three saddle points. These marked x's are the saddle points, the extrema of the potential. And you'll always get this valley. And this valley is the lowest value of the potential, and that will dominate the ensemble, and that is indeed the case. But as you increase beta, you'll notice that this valley lifts. And once it crosses this crosses the zero value, it basically shifts. The dominance of the saddle shifts. This is like a first order phase transition we encounter in statistical systems. But this is not of concern right now. This is an important physical point, very important. But what I'm concerned is what happens if you increase beta further. So soon enough, these two, this lifts further, and there's no additional extrema on the real line. And you only get one extrema of the potential on the real axis. And this situation can also be understood from the relation I gave you between beta and R plus. You just plot it, you see that beta has a maximum for real R plus. And if you take a beta above this, you'll always get complex solutions to this equation. You'll not get real roots. But what is the problem with this? As I began by saying that there are spurious contributions to these partition functions, and the spurious contributions are these complex ones, because what happens is that even though at small values of beta you have real solutions, there's a phase transition where the saddles exchange dominance, all this picture is fine. But if you keep on increasing beta, there's a point where the potential, the real part of the potential, becomes negative at these complex saddles. Because if the saddle is complex, the potential itself will become complex, but the real part is what governs the weight by which it enters the partition function, and it can become negative, which is to say that these complex saddles can come back to dominate the entire ensemble. Now, for various reasons, we don't expect this to happen. I cannot right now go into those reasons, but I'll have you believe me that this should not happen in a system like the one we are considering. So we have to explain this somehow. Now, I have a brief aside on saddle point methods, which is like we have an integral of this kind, right? The partition function is something of this kind where there's a large parameter lambda, and whenever you have a large parameter lambda, you expand around the saddles, you get a sum like this. But for a generic integration region or integration contour, you do not get all the saddles contributing. You have to decide which saddles contribute, and that analysis is sometimes referred to as steepest descent analysis in one variable. And the basic logic is that you need to deform this integration region in a way that you pass across the saddles along some steepest descent directions. And that's exactly what we'll do. So let's come back to the case in hand. We had this potential, and what I'm showing is for small beta, where the saddles lie on the real line in the complex R plus plane. Now, these dashed lines are basically the steepest descent directions. And the integration region I told you was this positive real line. And the decomposition of this positive real line in terms of the steepest descent lines is simple. You just take the right half of the red part and the full blue part to rewrite it as this combination. So this green thing never even enters the computation. For larger beta, what happens is that as these saddles merge and become complex for some values of beta, the steepest descent directions themselves also undergo a non-trivial change. And now the decomposition is simply in terms of the right half of the red contour, and you should express it like half of the full steepest descent contour. And this is the reason why these complex saddles do not contribute. This is from an analysis point of view, this is why they should not contribute. Now, since I have 2 more minutes, I'll just explain a more generalized version of this, where you, instead of a Schwarzschild spherically symmetric black hole, you consider a rotating black hole. And now the solution is parameterized by 2 parameters instead of just 1. And the black hole also carries an angular momentum because it's rotating. The thermodynamic description again involves changing these parameters into 2 intensive variables, beta and omega. Omega is some angular velocity potential. And then you have some macroscopic charges. And the goal is again to encode these in a partition function. You again write something similar. You have a Boltzmann weightage of integrating over these parameters. This integration region is actually not obvious to fix. In fact, there are some ways to fix it. I cannot go into the detail right now, but please ask me later if you're interested. And again, the intensive variables are set freely. And the saddle equations, once I evaluate the saddles of this integrand, I'll relate beta omega with r plus Na, and that will retrieve back the thermodynamic relations for the black holes. But there's again a higher subtlety here, that there are actually more saddles. There are not just the black hole saddles. Remember, in the previous case, we had the black hole saddles and some trivial saddle at the origin. Here, there will be a trivial saddle at the origin. There will be the black hole saddles, but there will be a lot of other saddles also. In fact, for the case in hand, actually, there are 14 saddles at least. So how do you pick which saddles contribute? And you again have to do some sort of a steepest descent analysis. It can be done, at least in this case, I can do it explicitly. But in a general situation, it can be trickier. And as I told you, this cycle has to be decided how to pick it. I'm not going into the detail, but it can be done. And the result of the analysis is as follows. So this is some, I'll just take 30 more seconds. If you plot, so this is on 4-dimensional space, right? The complex R plus and complex A space. But if you just limit yourself to the subspace, which is real A and real R plus, and plot it against in the complex plane, or in this 2-dimensional plane, you'll notice that for smaller values of beta, again, and some fixed omega, you get, this is the steepest descent contours, analog of the contour in 2 dimensions. The blue region is for the trivial saddle. It's not marked properly. Oh, it's the, yeah. So this blue region is for this trivial saddle marked here, and this red region is for the black hole saddle. And so you decompose your again integration region as some like this. And now as you increase beta, your integration region is fixed, and you notice that after some value, the full steepest descent direction is simply steepest descent region is simply corresponding to the trivial saddle. Again, these saddles merge and become complex. So, and the steepest descent directions undergo non-trivial change. So they don't occur in the decomposition of the integration region, and hence here also the complex saddles really just go away. They don't contribute they don't come in as spurious contributions. And that's the punchline of all of this analysis. And yeah, I'd like to just conclude with that. Thanks.
Kaustubh, for the interesting talk. Questions?
Can you go to the plot where you showed the steepest descent analysis?
The 2-dimensional one or 1-dimensional?
1-dimensional. Yeah. Can you explain which contour are you integrating over?
Yeah. So the integration region is the real line, and this is a complex R plane. This is the real line. This is 0.
Yeah, the green
it's very small.
is the steepest descent contour, right?
Sorry?
The green dotted line?
It's the steepest descent contour for this saddle. Blue one is the steepest descent contour for this saddle, and red one is the steepest descent contour for this saddle.
So your contribution from, will you get contribution from all the saddles?
No, so that's what I was trying to say. You will only get contributions from half of the red and the full blue one. You won't get anything from the green one. Even though it's a saddle, you won't get it's a real saddle, you won't get a contribution from that.
So initially your integration is from -infinity to +infinity?
No, 0 to infinity.
Oh, 0 to, oh, okay.
So the decomposition here is very obvious because you can just geometrically map it. And in fact, you can rigorously also argue it's that. The non-trivial situation is when you increase beta and the steepest descent contours are more complicated. But here also you can actually geometrically see that it's just this real line.
Yeah, okay. And in the 2D case, can you tell me what the contours were?
Yeah, that's a bit more hard to visualize even for me. Yeah, so what I'm plotting firstly is this. On the vertical direction, I'm plotting real values of A, and on the X direction, I'm plotting real values of R plus. There's a reason why I'm plotting only -1 to 1, but I'll not get into that. The point is that if you take this saddle, since there are 2 variables now, there'll be 2 steepest descent directions in R plus and A independently. And this is that region. It turns out that this region is entirely on this subspace, real A and real R plus. That's why I'm plotting this, because I cannot plot 4-dimensional things, barely plot 3-dimensional things. But yeah, but 2-dimensional things are easy to plot. So in this case, I can just plot this blue region and this red region for the others. This is the black hole saddle. I should have mentioned that more clearly. And this is relevant that you decompose your contour in this form, the integration region in this form. It's a 2-dimensional integral, so we shouldn't really call it a contour, but So this is the identical to the decomposition we had earlier. This is actually an implicit way of fixing the contour. But now that it's fixed, you can analyze the same situation for larger values of beta. And then you see, if you keep track of these steepest descent direction, that after a point, these things become complex, these black hole saddles. And that is when I'll call them a spurious contribution because of various reasons. And after that point, from a steepest descent point of view, the entire thing is just steepest descent direction for the trivial saddle. And that's the reason that these complex contributions, even though they occur as saddles and everything will compel you to tell that that is the dominant thing. But if you do a more careful analysis, they are not there.
Okay, thanks.
Questions? Okay, questions from online participants? If not, let's thank Kaustubh again.